Hello everyone. For the Physics 58E Spintronics lecture, I wanted to talk about the voltage-controlled magnetic anisotropy, which is a very interesting topic. In the literature, when we search voltage-controlled magnetic anisotropy, we can observe many different type of concepts based on this topic. First, I wanted to give you a brief information about these concepts in order to distinguish them. First concept is using piezoelectric substrates. As we know, when we apply voltage to a piezoelectric material, we can change its size. We can manipulate its dimension. If we fabricate a ferromagnetic structure on top of a piezoelectric material, and when we apply a voltage, we can apply a strain or stress to a ferromagnetic material. Because of this strain and stress, we can manipulate the magnetization direction of this magnetic structure. Based on this concept, we can fabricate magnetic memory devices. In another concept, we can switch the exchange bias direction by applying electric field or voltage. And in this concept, we need to use a multiferroic material. One of the multiferroic material is chromium oxide. And by field cooling the system under that electric field with different polarity, we can change the exchange bias direction either in positive or negative sides. In another concept, we can manipulate the structure of a material. If we apply a voltage, we can induce a magnetic phase transition through structural phase transition. This is one example that you can see from the literature. They used iron material here, and when the structure is BCC, it is providing ferromagnetic properties. When the structure is FCC, material providing antiferromagnetic properties. And this is another concept that we can control the magnetic anisotropy of materials by a voltage. In another concept, we can control the Curie temperature of ferromagnetic materials. And if the magnetic anisotropy is changing, we can observe something for ferromagnetic resonance, because ferromagnetic resonance is a powerful technique to analyze or characterize the magnetic materials anisotropy. If something is changing in anisotropy, we should observe something in fMR spectrums. In the next concept, we can switch the magnetization states from one direction to another one by applying voltage, and we can fabricate memory devices based on this topic. So as you can see, there are many different concepts that you can find in the internet, in the literature also. And I don't want to go deep into details of this three concept, but for my presentation, I will focus on this three concepts. Let's start with gate-controlled Curie temperature. In the 2011, Daiichi Chiba and his group has shown that we can manipulate the magnetic anisotropy and Curie temperature of a ferromagnetic material. In their studies, they used an MgO, cobalt, platinum, and tantalum materials for investigation. And this material is providing a perpendicular magnetic anisotropy. In order to apply a voltage or electric field, they used an insulating layer here. They used hafnium dioxide, and for the gate, they used gold in order to apply voltage. For the experiment, they applied DC current, which is constant, and they measure the Hall resistance as a function of temperature. First, they made experiments as a function of temperature. When there was no voltage applied, they observed this. This x-axis is showing temperature, and y-axis is showing the measured resistance. When there was no voltage, they observed this black curve. It is going to 0. We know that Hall voltage is related to perpendicular magnetic anisotropy of a system. If it is go to 0 as a function of temperature, we lost the magnetic perpendicular anisotropy or magnetization component here. So we can say magnetic material becomes paramagnetic at this temperature. So this is the Curie temperature of the system under 0 voltage. When they apply positive 10 volts, they observe this Curie temperature is shifting to a higher temperature. And when they apply negative 10 volts, they observe this Curie temperature shifting to a lower temperature. So this is very clear evidence that we can manipulate the Curie temperature of ferromagnetic materials by applying voltage. So what we can do with this information? If we fix temperature 300 kelvins here, you can see it behaves like ferromagnetic here. So by applying electric field with different polarities, we can manipulate the coercive field of hysteresis loops. We can enhance or we can reduce the coercive field of this hysteresis loops. And for the second, if we set the temperature between this 0 volt and negative volt here, 321 Kelvin here, if we apply negative 10 volts, this time we are at a higher temperature than the Curie temperature. Because of that, it provides a paramagnetic behavior here. And if we apply positive 10 voltage, now it is coming to here. We are in the ferromagnetic plane phase. Because of that, we can observe a hysteretic behavior of this measurement. So this is a very beautiful concept that we can manipulate the magnetic anisotropy and Curie temperature of a ferromagnetic material by applying a voltage. So the next experiment is the ferromagnetic resonance measurements. Here there is a spin transfer induced FMR technique. In this technique, there is a signal generator connected to a bias T, and there is a source meter is connected to a DC source input of this bias T. And this bias T is connected to an MTG device, and the rectified voltage or created voltage is measured by an analyzer here. So by adjusting, by tuning this DC voltage source meter, we can observe a shift in ferromagnetic resonance spectrums. Here you can see resonance condition, resonance frequency is shifting as a function of applied voltage. When we increase the positive side, the shift is shifting to lower frequencies. And when we apply negative voltages, the resonance frequencies are shifting to higher frequencies. So if we draw a graph for this experiment, you can see this resonance frequencies are shifting as a function of applied voltage with a very linear manner. So this is another clear evidence that we can manipulate the magnetic anisotropy of materials by applying voltage. In another concept, we can switch the magnetic easy axis between perpendicular state and inclined state. They used, and again, an MTG structure, and for the free layer, they used coffee bean material and MgO material here for insulating layer. And for the fixed layer, they used a coffee bean, and this is fixed by the cobalt palladium multi-layer structure. When they applied zero voltage, they observed this hysteretic behavior under the sweeping magnetic field along Z direction, this perpendicular to the film plane. And when they apply a -1 voltage, and when they sweep the magnetic field, again, they observe the hysteresis is enhanced. It means that something is induced in the hysteresis tropy, and magnetic anisotropy is enhanced here. And if they apply a +1 voltage, they observe no hysteretic behavior, but a hard axis behavior, indicating that this perpendicular magnetic anisotropy is switched to an in-plane state. They explained this phenomena by drawing energy density profiles. Here, there is a Stoner-Wolfert energy profile, and y-axis is showing energy or energy density, and x-axis is showing the angle according to positive z direction. 0 degree means a positive z direction, and 180 degree means a negative z direction. As you can see, under the zero voltage, it has a very symmetric energy profile, and it has two energy minimum. One is 0 degree, another is 180 degree. It means that if we apply, okay, let's think we are here at the positive z direction. Magnetization is looking a positive z direction. So when we apply a voltage, we can reduce this hard axis energy barrier as a function of this applied voltage. And if we define a critical voltage to totally remove this energy barrier, we can say this is very voltage critical. And if the applied voltage is lower than this critical voltage, we can reduce the energy barrier, and we can more easily switch the magnetization compared to this system. But if we increase the applied voltage to higher than the critical voltage, we can make a new energy minimum here at 90 degree, which means XY plane. It means that the XY plane becomes an easy plane. Because of that, if we apply more voltage than the critical voltage, magnetization is switching to an XY plane with a precision motion. So this is the explanation of this switching mechanism. So we can switch magnetic anisotropy from perpendicular state and to an in-plane state. So a question can arise here. Can we switch the magnetization by applying only voltage from one perpendicular state to another? Let's say this is positive z direction, this is negative z direction. If I apply voltage and remove the voltage, can we switch to the negative z direction? The answer is yes. Here, as I said, if we apply a high critical, if we apply voltage higher than the critical voltage, the magnetization is start to precess to XY plane. And if we apply a bias field here, the magnetization will precess around this bias field. And if we apply voltage, and it will go like this, and at the time that the switching is here, magnetization is rotated to minus Z side. If we remove the voltage, we can confine the magnetization at minus Z side. So we can switch the magnetization by applying only voltage. And this bias field can be applied externally or can be exchange bias structure or in-plane magnetic anisotropy structure added to the system. So this is the example for the switching mechanism. Here there is an MTG structure. The top layer is free to switch up and down sides, and this is the fixed layer, which is synthetic antiferromagnetic layers. And by applying pulse voltages, we can switch the magnetization state from parallel to an antiparallel state. So this is the switching probability, as you can see, and this is the time pulse width of the applied voltage. And the probability is 1 when the time is 1 nanosecond almost. So this is the experiment they did based on this concept. When they apply 1 pulse, they can successfully switch the magnetization state, and they read the resistance state of the device. And they did, again, they apply 1 nanosecond pulse, and it will switch here again and again and again. And there is a repeatable and very stable device that can be controlled by only applying voltage. So this is a very beautiful device that can be make memory by using this concept. Here, there is a schematic illustration for the memory bit cell. This is the memory device. It is connected to a bit line, and it is connected to a voltage pulse control. And there is a word or write line here connected to a trigger transistor. And we can read the output by measuring the resistance of this device. Here, an example again, when we apply 1.2 nanoseconds, we can switch the magnetization from an antiparallel state to a parallel state. Again, 1.2 nanosecond pulse is applied. It can switch from perpendicular state, parallel state to antiparallel state. If we double the pulse time, we can observe a double switching from antiparallel to parallel and parallel to antiparallel states. So this is very beautiful memory device that we can fabricate by using this concept. So why we need this voltage controlled magnetic anisotropy? We already have STT-based MRAMs, SOT-based MRAMs, also optical switched activated memory devices, also solid state devices like this. Answer is this. When we apply voltage, actually we don't apply current to the system. In these STT MRAMs, the energy required for writing a bit is almost 100 femtojoule per bit, and the switching is taking time. At this time interval, almost 10 nanosecond. And this is the advanced STT and optimized STT MRAMs. Compared to this one, this is the last concept I mentioned. Compared to this STT MRAMs, the energy required for writing a bit is very low compared to this one. Also, switching is very fast. So we can fabricate faster and low energy consuming devices by using this voltage controlled magnetic anisotropy. For the conclusion, we discussed about the manipulation of grid temperature and hysteresis, and we discussed the shift in resonance frequency as a function of applied electric fields. And we discussed the magnetic easy axis switching between in-plane and out-of-plane. And we discussed pulse voltage induced magnetization switching. And we discussed a device based on this concept. That's all I wanted to talk about for this voltage controlled magnetic anisotropy. Thanks for watching.